Okay, good morning, everyone. My name is Leto Baxevanaki, and today I'm going to present a structured concurrency framework that my team in Bitmovin built. So we built this framework so that we can develop a video player on top of it. So I will explain why we took this route and what are the benefits that we finally saw from this solution. Okay, first, let's take a look in a couple of challenges that nowadays video player developers face. Okay, first, I would like to present a complex playback use case, a workflow, a seek operation in an SSAI-enabled video stream. So what does the player need to do in this case? The player has to ensure that the manifest is up to date in the case of a live stream. He has to start downloading the media segments to the targeted position, then potentially has to reconfigure the decoder if we have to switch between DRM and non-DRM content, and potentially set up a DRM license workflow. And then, after the player starts all these processes, the user changes his mind. He wants to cancel the seek operation. So all of these processes have to be cleaned up. Quite complex. The other topic I would like to address here is the challenge of the custom use cases. So the player comes with a core functionality, and it is rarely the case that it meets the customer case, right? So customers have different kinds of segment formats. They may have non-standard encryption formats, proprietary manifest files. So all of them have to be addressed in the player. Okay, so let's sum up the challenges. So first of all, we have the asynchronous operation issues. Unpredictable execution may lead to cause race conditions. Also, it is hard to manage the cancellation in a clean way. The second point is how can we handle adding new features without breaking the functionality. And many of the players being used currently, they exist 5 or 10 years, so they could have a monolithic architecture. Okay, so I would like now to present what are the requirements that we set in the team in order to build this new player and this new framework. So we said that we need a framework that has a plugin system and an effect system that is fully structured concurrency aware. What is structured concurrency? So it's a programming paradigm that respects a couple of principles. So, I mean, the main idea is that the parent process must take care of the child processes. It has to clean up any child process before it terminates. So this is the difference. In the second graph, it is the structured concurrency paradigm that respects these rules. Okay. So, having this in mind, what would be the key features of the framework? So the framework that we built, we named it Phoenix. And the key features are that it has a structured concurrency-aware plugin system. It supports dependency injection and also has an effect system for handling asynchronous operations. Let's take a look at some of the core components of the framework. It will be high level. Just wanted to give you an idea. So the fundamental execution unit of the framework is the task. The task is a type of function that takes 2 parameters. So the second parameter is the context that provides a function that you can execute or start a child task. Using this way, structured concurrency principles can be fulfilled. So the framework is built in a way that it executes packages. Packages are code modules that define functionality. And this is the way you can extend the functionality that is running in the framework. The package has dependencies and exports, and it needs an execution context. The execution context has a registry. So the registry is a map of all the components that actually run in the framework at the current point of time. Another concept that is being used in the framework are effects. Why do we need effects? Because there are certain things that are happening outside the execution tree, outside of the framework, like we call browser API. There are video element events. These need to be bound in the execution tree. So this is the mechanism that we're using. As an example, we have the state effect. So we have an effect that we call it state effect, and it is actually depicting the state, and we can really solve the problem of the seeking operation because we can model a seek operation through the state object. And the seeking operation can subscribe to the state, to the seeking state, and be notified for any of the changes. Okay, enough with the framework. So let's see what we did. So our primary goal was to build a player, right? A new generation player, and we did it. We used this framework. The new player is Player WebEx. It is a product of Bitmovin. And what did we earn? Extensibility. So adding a new feature is really fast. We did, like, for an example, we added a plugin that provides single instance, multi-source, multi-view experience in a couple of days. We could also integrate proprietary streaming formats effortlessly. And also, the other big benefit here is a thin player, because you can tailor the size of your player depending on the use case. So this is a big advantage, especially for short form. And what we also saw after building this player were huge improvements on the metrics, on the performance. I will take here as an example startup time. We saw that startup time was reduced radically. And why is this? Because using the structured concurrency and the state-driven implementation, we eliminate redundant execution, and the cleanup is done in a controllable way. So I'm claiming reduced startup time. Of course, the tests can be subjective. We tried here to be as much subjective as we could. We ran the same test on a Chrome browser with local assets, but using a library to control the network bandwidth. So the test was the same for all the players, and we also controlled the timeout. As you can see here, PlayWebEx outnumbers other open source players. So, to conclude, structured concurrency enhances the performance and the robustness because it provides a way to control the execution, ensures the plugin system provides more flexibility and scalability, and simplifies the video player development. If you would like to read more about it, you can scan this code. There are a lot of articles about this project and product. And there is also a repository with templates of how you can build your own plugins and extend the player. Thank you.
Thanks, Leto. Any questions for this talk? Yes, Daniel.
Thank you. Very interesting. You had these startup times comparisons, I think, on the second to last slide. Did you also consider other factors like startup quality, like the buffer target at the start? Because there are multiple things that play a role in order to compare how a player performs. So.
Yes, we did measure also other metrics, right? Like seeking time, switching between sources, and yeah, quality startup time can be ABR related, right? And it depends on the use case. With this new player, there are new use cases that we can address, short forms, clips. So I think for the quality, I'm not sure if we could really compare, but we did take other measurements as well.
Yeah, I know what I meant is like if you compare players and their startup times, maybe one player starts at the highest rendition and the other one starts at the lowest rendition, and then you're obviously a bit faster downloading stuff. So I think you need to take that also into account if you compare player performances.
Yeah, it's okay, different ABR.
Yeah.
Thank you. Another question? No? Thanks, Leto, again.
Thank you so much.
Yeah.